Okay, so we're going to get started with classification problems tonight. And the problem we're going to work on is predicting the gender of a person based on other characteristics. And this lecture is only going to cover two types of models, k-nearest neighbors and naive Bayes. And I'm going to use the CDC data from before partially so that this document will be a standalone document, and partially because it contains the some cleaning tasks for the data that are important to do before you get into machine learning. So let's go forward to task 1, where we really start doing tonight's work. The first thing is to scale the data. Height and weight need to be scaled so that both are on a 0-to-1 scale. This is super important for k-nearest neighbors because you're computing distances based on the Euclidean formula, and if you don't put things on a common scale, then the activity is really dominated by the thing that has the largest range. And height is obviously something that's constrained in range. You start from about 4 feet and go to a little bit over 6 feet, which is like 48 inches to 72, or maybe a little bit above 72 inches. Weight, on the other hand, goes all the way from close to 50 to 500. So the huge range in weight demands that we, compared to height, demands that we get these things scaled. So here what I've done, I've taken the mean before doing the scaling and the range before doing the scaling, and the same thing with the range of height. And you can see the differences there. And then this is the formula, which is really out of the DataCamp course. Basically, we'll take all those things and rescale them to be 0, 1. Here you can see afterwards I print the range. And for both of them, they're not on a 0, 1 scale, and the weight, the mean value of weight, is 0.23. Okay. So, task 2, split the data. We want to split our data into train and test, and we'll build a model on train, evaluate its performance on test, just like we did last week with regression, and randomly select about 75% of the data for train and 25% for test. And you can follow the process in the MountainZooML course in DataCamp to create train and test subsets. So pause the video and do that, then come back and restart the video again when you've completed that work. Okay, you're back. I hope you've completed the work. And this is the way we do it. This is the code that you've seen before. I put a seed in here because I don't want to be looking at slightly different numbers every time I run this thing. I want to make sure that the numbers remain the same. So this, even though I'm generating random numbers, I use a seed to make sure that the random numbers are the same from run to run. Okay. Task 3, KNN Model 1. Use select to create train underscore A and test underscore A. And these data frames contain only gender, height, and weight in that order. And I want you to follow the procedure in the DataCamp course to create a KNN model for gender with K equal 1. And build the model using train, measure it on test. Note that the variable gender, which has column index 1, must be removed from the train data frame and placed in a separate variable called gender. And you can follow the model the way sign types was used in the DataCamp course. And yeah, just follow the sign types model for doing that. And then I want you to compute the accuracy of this model using the procedure in the DataCamp course. Okay, so that's a pretty good hunk of work to do. So time to get to work on that. And of course, while you're doing your work, stop the video and come back here when you've done your work. Okay, you're back. I assume you've done the work. So I made train A. I just restricted it to gender, height, and weight. And test A is the same thing. It's the test data frame restricted to gender, height, and weight. And I set this variable gender to be train underscore A $gender. This is just the same way that sign type was used in the example thing. And then I call this K1. You obtain K1 by applying K and N. So train is train underscore A with all of the columns except for the first column, because that's the one you're trying to predict. And test is test underscore A, everything but the first column, because that's what you're trying to predict. And the class, which really is the basically just the gender column removed from the train A data frame. And then we take the mean of test underscore A dollar star gender is equal K minus 1, K underscore 1. And this means this the mean value of a Boolean expression gives you the proportion of cases for which the Boolean expression is true. So what you're asking for is the fraction of the time in which the K and N with K of 1 got the correct results. And it says 0.8489. And I'm still keeping track of train underscore A $ weight. And I probably should have dropped that. That was for a debugging problem that I was working on earlier, but it's still there. It won't do any harm. Okay? So take a look at that. And of course, pause the video, stop, look at it. Make sure you understand the way I did it. Okay, ready to go on? Task 4. Repeat the process to create and measure the performance of a model, the same model, but use K equal to 5. Okay, that's a fairly simple task. Just copy the code from the previous model, and all you have to do is insert another argument into the call to KNN, because the default was 1, so you don't find a specification of K in the default model. Okay, go ahead and do that. Stop the video while you're working. Come back and start it again when you're done. Okay, I assume that you have done your work. And here, I didn't have to do all of the things that I did in the first model, but this is the critical difference. I took those 2 lines of code out, and at the end, I put in this extra argument, K equal to 5. And then I said, for what fraction of cases was it true that the 5 variable model produced the correct results? And I got 0.854. Not bad. Okay. Task 5, try K equals 50. And here I didn't even split it off into a second thing. That's getting too easy to do that. And we got 0.858. Is that any better? Let's go back and look at the previous slide. Before we had 8548, 8548. And now we have 858. So yeah, from going from 5 to 50, we improved. We got a better fit, just marginally. Okay. What should we do next? Well, I think the next thing we should do is go ahead and shoot for the moon. Try a much bigger value of K. Task 6, try K equal 100. And here I didn't even stop the video for you. The only difference is that I have K equal 100 instead of K equal 50. And if you remember what we had last time, it was 0.858. Now it's dropped to 855. So that cost us a little bit in performance, but you notice all these measures of performance are not changing a whole lot. Okay. Task 7, let's stick with K and N, but add some variables to the mix. Create data frames, train underscore B and test underscore B, and add gen health, smoke 100, and X or any. And try K values of 1, 5, 50, and 100. And you notice that I violated my assumption. I violated my instructions when I did this. All I did was make train B. I added smoke 100 and Xer any, but I didn't add Gen Health. And the reason is that I'd have to do some extra work with Gen Health, and I'd have to produce dummy variables on it. Most of the procedures in R, in machine learning, will automatically take a categorical variable and automatically produce the dummy variables for it. But KNN, this particular variant of KNN, doesn't do it. So I chose not to include that. Okay. Anyway, here's what happens. I got an 834 for accuracy. That's not as good as what I got with just the simpler case where I had gender and height in the model. So adding all those extra variables didn't do any good. I do get a little bit better with when I step up to 5 and up to 50, but again, when I step up to 100, the performance drops just a little bit. Not really noticeably, but it looks like you can see the performance deteriorating between 50 and 100. And so far, the most successful model we've had was with height and weight only, and k equal 50. The baseline, task 8. Our data is not evenly divided by gender. Use the simple table command on train and test to see the true distribution of gender. Divide by n rows so that you're getting proportions instead of absolute counts. So stop this video and do the work and come back. Okay, you're back. Hope you did the work. So here's the table command, table of train $gender divided by n row of train. And I see that what I've got is the data frame, both the train and test. Fortunately, it's appropriate that they turn out about the same, are about 52% female and 48% male. So the smart thing to do, if you're making a choice, you had to randomly guess a person's gender, knowing absolutely nothing about them. Your best bet would be to say this person is a female, because that way you'd be right 52% of the time. On the other hand, if you said this person is a male, you'd only be right about 48% of the time. So that's a baseline. Think of this as an absolutely no-brainer guess, and you have to compare any model that you produce with the no-brainer guess, 52% accurate. Okay? So task 9, again, this is where you start to have to do some heavy work again. Let's consider using one of the categorical variables, say smoke 100, as a predictor of gender. And I want you to use naive Bayes with this variable only, and measure the accuracy on the test data. So stop the video and do your work and come back when you're done. Okay, you're back. I assume you're done. So let's go ahead. The specification is really simple. Naive underscore Bayes. There's a formula, which is gender depends on smoke 100, and data is train. And NB1 underscore predict is predict with using the model NB1 and applied to the test data frame. And our accuracy is the fraction of cases in which it is true that NB1 underscore predict is actually equal to the true value of gender in the test data frame. And we get an accuracy of 55%. So you might say 55%, that's pretty good. I'm right 55% of the time. Remember that you are right 52% of the time, even if you had absolutely no information at all. Okay? So it didn't really add, it added something to our ability to predict things, but not a whole lot. Task 10, add a second categorical variable, gen health. Does this improve the accuracy? Okay, and again, I'll stop here. You'll stop the video, do your work, and do that again, okay? Okay, you're done. So let's take a look. The only difference from the previous code is that now I'm referring to everything as NB2, and there's this plus gen health to the right of the tilde. Everything else is exactly the same. And I compute the accuracy, and I get it 0.550. And it's actually just a slight decline. And you might think that's impossible. If you gave it more information, why does it do even worse? Well, this happens. You might think it's mathematically impossible, but really remember that what you're doing is building a model on one data set and testing it on another data set. And this is the general overfitting problem that you're seeing, just in a very, very, very mild case of overfitting. But it's telling you that no, adding gen health didn't really do anything to that model to predict it, to improve its predictive accuracy. Task 11, let's use a quantitative variable, height. Do this with naive Bayes and measure the accuracy. Okay, I will pause, I'll stop talking, turn off the video, come back and watch the video again when you're done. So here we have NB3, the third variant of naive Bayes. This time it's gender tilde height, which is a quantitative variable. Same setup, it's really just a minor difference from what we did before. And the accuracy is the fraction of cases for which this Boolean expression is true, namely that the prediction made by naive Bayes 3 is the same as the true value of gender in the test data frame. And our accuracy is 0.8394. And you can see that that's it's much better than the simple categorical model that we tried. There's something worthwhile there. But it's not as good as the best of the KNN models that we did. So let's see if we can improve on that. Add a second quantitative variable, weight, then measure the accuracy. And I'll pause, I'll wait here while you're doing that. Of course, you're going to pause the video and take a few minutes to do whatever you do with your computer to see the result. Okay, you're back. I assume that you have done your work. So the change, you can see that I added weight here, so it's height plus weight on the right-hand side. And we now call everything, we label everything with a 4. And again, we compute our accuracy as before. And 0.837, a slight loss of accuracy with a more complex model. Again, you see that making the model more complex does not necessarily make it better. You could say it didn't really do any substantial damage to it, but it didn't do a whole heck of a lot of good. 13, try weight alone and compare the accuracy with the previous results. So pause the video while you do this, then come back and take a look at what I have to say about it. Okay, you're back. Let's take a peek. Here's just weight as on the right hand side of the model, and you can see that this is really definitely weaker than height. So height is a better predictor of gender than weight is, although the two are somewhat correlated. So the best model of this set is clearly height alone. And the final question, this is always the final question after a machine learning exercise, we did several variations on two types of models, KNN and naive Bayes, and which was the best of all of these? Do you remember? Well, it was the KNN model with an N of 50. So that sums up what we've done with these two types of classification models.